Hello, in this video I'm going to explain binomial expansion, which incidentally means I'll be talking about the binomial theorem and the Pascal's triangle. This video is first in a series of 3 videos and therefore the easiest. The target audience is basically anyone with the desire to learn, but from an academic perspective, high school students and undergraduate students. In the next video we'll talk about the multinomial theorem, which is geared toward graduate students, and in the final video we'll delve into 3D figures and some super cool formulae. First of all, what is a binomial? Bi as in two and nomial from polynomial. Therefore, a binomial is a polynomial with 2 terms. So, a binomial is basically the addition or subtraction of 2 terms. A plus b is a binomial and so is a minus b. We won't be worrying about a minus b because a plus b includes it. I know that doesn't sound right, but let me explain it using this example. Here you might compare it with a minus b and say that a is 2 and b is 5, which is perfectly correct, but you can also compare it with a plus b by rewriting it like so. 2 plus negative 5 squared is the same as 2 minus 5 squared. Now here you compare it with a plus b. So a is 2 and b is negative 5. This is also the reason why we don't discuss negative a plus b or negative a minus b. Okay, with that out of the way, let's look at some binomials raised to some power. A plus b quantity raised to 0 is 1. That is a property. Any number raised to 0 is equal to 1. Now, I'm required by the law of mathematics to inform you that this property is true only if the number itself is not 0. Because 0 raised to 0 is actually undefined. This topic gets into calculus and is completely unnecessary for this video. Next, a plus b raised to the first power is a plus b, but I'm going to write it as 1a plus 1b. Typically, we don't write 1 as the coefficient in mathematics, but I'm going to write it here and the reason will be apparent very soon. Next, a plus b squared is a squared plus 2ab plus b squared. In India, where I grew up, students are expected to memorize this as a formula because math instructors are like, pop quiz.
Rule number 8. What is a plus b the whole squared?
It is a squared plus 2ab plus b squared. I am not one of those who memorizes every formula. I should be ashamed. In fact, I'm just good at deriving formulas very quickly. Let's see what would have happened if the instructor had asked me.
Rule number 12. What is a plus b the whole squared?
Square is basically number times itself. So, a plus b squared is a plus b times a plus b. That is a times a plus b plus b times a plus b, which simplifies to is a squared plus b squared plus 2ab. After doing this derivation tens of times, it just gets committed to memory. And if the operation is computationally intense, I grab a piece of paper and derive the formula by scribbling. Anyway, that was about India, but here in the United States, they use something called the FOIL technique. And I can go off on a rant here, but I'm planning to make a separate video expressing why I believe FOIL is one of the worst things that students are taught over here. Anyway, a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. If you don't have this stuff memorized, then you can distribute this expression like so and arrive at the same final step. But if you try this on your own, you'll realize that it is a load of work. I promise I don't enjoy tracking this, but I want you to try to simplify a plus b raised to the 4th power by distributing this expression properly. I know most of you did not try it. Shame on you for being so lazy. But if you did, then here are 2 of the potential things that you learned. Firstly, steps increase exponentially. And secondly, if you make one mistake, it cascades all the way to the end. So it is quite clear that this method is very inefficient. Let's discover something better together.
Transition.
If you look closely, there is actually a very nice pattern going on here. There's a pattern with the numbers, that is the coefficients, and also a pattern with the variables. Let's start with the pattern for coefficients. And to see it clearly, I'm going to create a similar table but without the variables. So on the left column we have the powers, also known as index or indices for plural, and on the right we have just the coefficients. But I have arranged the numbers in this triangular pattern. It is a simple yet interesting arrangement of numbers in the form of a triangle where every number is the sum of the two right above it. For instance, take this 4 here. It is the sum of this 1 and this 3. This 6 over here is the sum of this 3 and this 3. This triangle has a name in mathematics. It is called Pascal's triangle. You probably guessed that this is the case because some ancient mathematician named Pascal discovered it, and your guess is actually pretty good but still lacking, so let me fill you in. Blaise Pascal is a French mathematician who lived in the 1600s, but Chinese, Persian and Indian mathematicians had been using this triangle centuries before Pascal was even born.
Stop ranting, Viraj. You can make a separate video for that.
Okay. Returning to mathematics. This property is incidentally called the Pascal's identity. At this point I would like to tell you that I haven't closed this triangle because Pascal's triangle does not have an end per se. You can follow this pattern and keep creating consecutive rows. I want you to create the next row by following this pattern. 1, 5, 10, 10, 5, 1. Simple, right? And if you wanted, you could find the 6th row, the 7th row, and keep doing this forever. And just a side note for those that are super curious, in mathematics such operations are said to have a countably infinite number of steps. Yes, there are different sizes of infinity. Check the link if you want to learn more. The Pascal's triangle is full of interesting patterns like triangular numbers, powers of 2, powers of 11, the Fibonacci series, and lots more. Again, for more information, check the link in the video description. Okay, before jumping to the next phase of the video, I'm going to very quickly talk about two topics, factorials and combinatorics. Now, don't worry, even if you know nothing about these topics, you just have to remember a couple of things that I'm about to tell you. First of all, factorial is represented by the exclamation symbol, and the formula is n factorial equals n times n minus 1 times n minus 2 all the way up to 1. That might look scary, but the application is quite simple. Trust me. 5 factorial is 5 times 4 times 3 times 2 times 1, which is equal to 120, and 0 factorial is 1 by definition. I'm not going to explain why 0 factorial is 1 because that is a topic that deserves its own independent video. Go check out this video by Eddie Wu if you're curious. Okay, now moving to combinatorics. This thing, it stands for n choose r, or as I like to call it, NCR. In mathematics, you can find chapters or even books on this topic because combinatorics is very extensively used in probability and statistics. But we don't need any of that for this video. We just care about the formula. It is n choose r is equal to n factorial over n minus r factorial times r factorial. So I just want you to know these three things: n factorial expansion, 0 factorial is 1 by definition, and the combinatorics formula. Here's another side note for the curious ones. All four of these are the same thing represented differently. Textbooks here in the United States use this representation, and scientific calculators use one of these two representations. And finally, this one is what I used back when I was in India. Anyway, for the purpose of this video, I'll be using only this representation. Now, let's go back to our Pascal's triangle. This exact information can be presented using the combinatoric symbols like so. Don't believe me? Okay, let's see it in action by picking any number from this triangle and checking if it is equal to the corresponding element from this other triangle. How about 6 from this one? The corresponding element is 4 choose 2. We'll have to use the formula to simplify this. 4 choose 2 equals 4 factorial over 4 minus 2 factorial times 2 factorial, which is equal to 4 factorial over 2 factorial times 2 factorial. 4 factorial in the numerator simplifies to 4 times 3 times 2 times 1, and the 2 factorial in the denominator is 2 times 1. So in the numerator we have 24 and in the denominator we have 4. That simplifies to 6. And you can use this process to check a couple more on your own, but since I'm recording this as a video, I'll stop at this and say that these two triangles are equal. So we have figured out the pattern of the numbers, which are the coefficients, but we still have to find the pattern for the variables. Don't worry, the pattern for the variables is very distinct. In fact, I'm going to ask you to pause the video and find it on your own. I'll just copy this a plus b cubed equation to this section over here. We know that the coefficients come from this row of Pascal's triangle. Now, if you look closely, the pattern that a follows is that it starts at 3 and keeps decrementing by 1. Some of you may be wondering what happened to a in the last term. Well, a raised to 0 is 1. So this expression is the same as this. 1a cubed times b to the 0 plus 3a squared b plus 3ab squared plus 1 times a to the 0 times b cubed. And the pattern for b is that it starts at 0 and increments by 1 until it reaches 3. So a plus b cubed gets its coefficients from this row of Pascal's triangle, and a starts with a power of 3 and then a squared, then a raised to 1 and finally a raised to 0. B, on the other hand, starts with a power of 0 and then b raised to 1, then b raised to 2 and finally b raised to 3. Wow, that was quite a lot. But with this information you can expand a plus b raised to any natural number power. A couple of facts for you to remember. For each term, the power of a plus the power of b is equal to what you raise the binomial to. As you can see, 3 plus 0 is 3, 2 plus 1 is 3, 1 plus 2 is 3, and finally 0 plus 3 is also 3. Second fact is that the total number of terms is 1 more than the power of the binomial. This was a plus b raised to 3, therefore its expansion has 3 plus 1 terms, well, 4 terms. How about you try to raise a plus b to the 7th power manually? There is an obvious problem with this method, and if you actually try to do what I asked you to by raising a plus b to the 7th power, then you most likely experienced it firsthand. In order to find the required row, you had to find all the previous ones too, and if you made any mistake, it cascaded down all the way. So clearly this method is better than the previous one that we discussed, where we used distribution, but still not the most efficient one. So how do we solve this issue? By using the other version of Pascal's triangle, the one that had combinatoric symbols instead of numbers. Let me explain. Using this combinatorics method, we don't care about the previous rows. We know that the required row is 7c0, 7c1, 7c2, all the way up to 7c7. And in order to find the numeric values of these quantities, we can use the formula or even the NCR function, which you can find on any scientific calculator. This way, we are completely independent of the previous rows. Now, you just have to align these coefficients with their respective variables. A starts at the maximum, which in this case is 7, and decrements by 1 until it hits 0, whereas B starts at 0 and increments by 1 until it reaches 7. Now you just have to put all of this stuff into one equation, and there you have it, the binomial expansion of a plus b to the 7th power. This is quite self-explanatory, but let me put this out there. This method of combinatorics is also resistant to that cascading effect that we discussed, where one mistake messes up everything. All things considered, this combinatorics method is the way to go in order to expand any binomial. Mathematicians love to put things in a general form. You have probably seen the general form for quadratic equations, linear equations, matrices, etc. So why not put this idea into a general form? A plus b to the nth power, where n is any natural number, like 55, 100, or even 500. Let's do this in pieces. First, just the coefficients. Using the combinatorics method, we know that the coefficients will be nc0, nc1, nc2, all the way up to ncn. Now let's look at the variables. We know that a will start at the maximum, which is n, and then keep decrementing by 1 until it reaches 0. So a raised to n, then a raised to n minus 1, then a raised to n minus 2, and all the way up to a raised to n minus n, which is essentially a raised to 0, which in turn is 1. B starts at 0 and increments by 1 until it reaches the maximum, which in this case is n. So b raised to 0, then b raised to 1, then b raised to 2, all the way up to b raised to n. Now we just have to put these things together in one equation. A plus b raised to n is nc0 times a raised to n times b raised to 0 plus nc1 times a raised to n minus 1 times b raised to 1 plus nc2 times a raised to n minus 2 times b raised to 2 all the way up to ncn a raised to 0 times b raised to n. This incidentally has a name in mathematics. It is called the binomial theorem. Most books use something called proof by induction to prove it, and I'm planning to make a separate video just proving the binomial theorem using induction. I'll put a card up here just in case you're interested. Anyway, most textbooks also take it one step further in terms of simplifying. They do it by using the summation operator. To incorporate summation into this equation, we need to find another pattern, which I'm sure some of you have already spotted. But those that haven't figured it out, here's a hint. Try to relate the power of A to its combinatorics symbol. Likewise, try to relate the power of B to its combinatorics symbol. Okay, the power of B is the easier one. It basically gets this number. As for the power of A, it is always this number minus this number. And using this newly acquired information, we can rewrite this equation of binomial theorem like so. Summation r goes from 0 to n of n choose r times a raised to n minus r times b raised to r. If you understand this, awesome. But if you do not have the foggiest idea of what this is, that is totally fine because I did not even try to explain it. The idea is quite simple. My aim is to explain binomial expansion using the binomial theorem, and you don't need to know this summation stuff to understand and to use the binomial theorem. But still, I'm willing to do a sloppy job here. This means r takes integral values from 0 all the way up to n, and after each value you put a plus sign. Since r starts at 0, you put 0 in place of r, and you get nc0 times a raised to n minus 0 times b raised to 0. Then you put the plus sign and then the next value of r, which is 1, and plug it in and keep doing this process until you reach n. You get this expression, which is the binomial theorem. That is all that I have for you for this video. I'm going to create a video where I solve a couple of problems using the binomial theorem just to give you an opportunity to apply this new knowledge. And originally the idea was to include it in this video, but this one just got too long and therefore I decided to separate it. I'll be posting a link in the video description with resources and additional interesting stuff. If you enjoyed the video, consider becoming a subscriber, give this video a thumbs up, or even turn on the bell icon. And as always, thank you for watching.